So we continue the exercises. So we are now in number 11. So step functions are dense in L1 0 infinity. So L1 0 infinity is the interval strictly positive in R, and L1 is the space with the Lebesgue measure, and therefore we want to show that step functions are dense. Now what is a step function? A step function is a simple function. So phi is a step function. This is sigma alpha I chi of ei. I equals some 1 to k, but now ei are intervals. So this is a step function. Okay, so this is such functions. So these are not just, they are special simple functions, so much smaller than simple functions as a set, and we want to show that this is also dense in L1 of 0 infinity. So solution. So let us take f non-negative, f continuous on AB. Okay, so we are taking a fixed finite interval. So then you take a partition P of this interval. So this is equal to A equals x naught less than x1, etc., less than xn equal to B. Okay, and you set mu of P, or let us say L of P, if you like, is the maximum length. So this is equal to maximum 1 less than equal to I less than equal to n mod xi minus xi minus 1. Okay, so then you have that if xi is a point in xi minus 1 xi, then the Riemann sum sigma I equals 1 to n f of xi xi minus xi minus 1 converges to integral a to b f of x dx. This is limit n tending L of p tending to 0. So you take all possible partitions, the maximum should tend to 0, so the partitions become finer and finer. Then these Riemann sums we know convert to the Riemann integral, but we are dealing with continuous functions, therefore Riemann-Lebesgue integral are all one and the same. Okay, so then if you choose, let us fix xi for instance to be such that f of xi equals minimum of f of x belonging to xi minus 1 xi. So just to fix ideas, you could choose anything you want to choose like this. So then you have that f is greater than or equal to sigma I equals 1 to n f of xi chi of xi minus 1 xi. So this is a step function. Okay, so this is a step function, and you have that. So this will imply that integral mod f over AB. So the integral is over AB of sigma f of xi chi of xi minus 1 xi dx. This is nothing but, I don't have to put the mod because I have taken the minimum. So this is equal to integral AB f minus sigma f of xi chi of xi minus 1 xi dx, and this goes to 0 by this condition, because the integral of the chi is nothing but the measure which is the length of the interval, and therefore you get that this tends to 0. Okay, so you have that sigma f of xi chi of xi minus 1 xi tends to f in L1AB. Okay, so this is so now if you take f to be an arbitrary continuous function, then you write as f equals f plus minus f minus, and then for each of them you can find a step function, and therefore there exists a step function phi n which converge to f in L1 AB. Okay, so now if f is in L1 of 0 infinity, there exists a g in CC of 0 infinity, continuous function with compact support, such that norm f minus g in L1 is less than epsilon. Then let the support of g be contained in some compact interval AB, then there exists a step function phi such that norm g minus phi in L1 is less than epsilon. Therefore, there exists, that implies that norm of f minus phi in L1 is less than 2 epsilon, and that proves that step functions are dense. Okay, so 12. So this is called the Riemann, one of the versions of the Riemann-Lebesgue lemma. Okay, so let h be a function from 0 infinity to r, bounded and measurable, such that limit of c tending to infinity 1 by c integral 0 to c ht dt equal to 0. So h is bounded, so on any finite interval you can integrate it, it's integrable. You are taking the average, so you are taking the integral over c dividing by the length of the interval, so that is nothing but the average. So the average of this function as the interval becomes larger and larger tends to 0. Okay, so A, show that if f equal to chi of AB, AB contained in 0 infinity, then limit as omega tends to infinity of integral 0 to infinity f of t h of omega t dt equal to 0. Okay, and B, deduce same result for all f in L1 0 infinity. So solution A, so f equals chi of AB. Okay, so what is integral 0 to infinity f of t h of omega t dt. So this is equal to integral, because f is chi of AB, so this is just the integral from A to B h of omega t dt. Okay, so you just f is 1 on that interval, and therefore it's just this, which is equal to, if I make a change of variable, this is equal to 1 over omega integral a omega to b omega, okay, of h of s ds. So this is just change of variable. So this is equal to 1 by omega integral 0 to b omega h of s ds minus 1 over omega integral 0 to a omega hfs ds. So I can put b omega here and put A omega here. Okay, so this gives you the average, and you know that as omega tends to infinity, A omega, B omega tend to infinity. So each term tends to 0 by the given hypothesis, and therefore you have that this goes to 0. Okay, so that proves the part A. B, if so, A implies true for step functions. It's true for every characteristic function, and therefore by linearity it is true for any linear combination of them. So it's true for step functions. So if f is in L1, there exists a g step function such that norm of f minus g L1 is less than epsilon by the previous exercise. So mod integral 0 to infinity f of t h of omega t dt is less than or equal to integral 0 to infinity mod f minus g h of omega t mod dt plus mod integral 0 to infinity g of omega h of omega t, sorry, g of t h of omega t dt. So this is f of t minus g of t. So if you like, mod f of t minus g of t. Okay, so the first term h is a bounded measurable function, so that is less than or equal to m. Now you get integral of mod f minus g, and that is the L1 norm, and therefore that is less than epsilon. Okay, so that first term is less than epsilon, and the second term, of course, g is a step function, therefore this goes to 0 as omega tends to infinity. Therefore you can make this arbitrarily small for omega tending to infinity, and consequently you have the result. Okay, so next 13 A, let A be contained in 0 infinity be a finite interval. And fn t is cos n t and gn of t equals sin of n t. Then fn tends weakly to 0, gn tends weakly to 0 in Lp of AB for all 1 less than or equal to p less than infinity. So that is solution. So AB is finite interval. So Lp of AB is contained in L1 of AB because it's finite measure space, and therefore any bigger Lp is contained continuously embedded in a smaller Lp. Okay, so now you take f tilde extension by 0 outside AB to 0 infinity. So you extend it. So then you have f tilde belongs to L1 of 0 infinity. So if you take ht equal to cos t, then what is mod 1 by c integral 0 to c cos t dt? This is nothing but mod sin c by c, which is less than or equal to 1 by mod c, and that tends to 0 as c tends to infinity. Okay, so similarly 1 by c integral 0 to t sin t dt is less than or equal, is nothing but 1 minus cos c by c, and that is less than or equal to 2 by mod c, and again that tends to 0. So h equals sine t, h equals cos t, they satisfy the previous properties of the function h given in the previous exercise. So by exercise 12, we have integral 0 to infinity f tilde t cos n t tends to 0 and integral 0 to infinity f tilde t sin n t tends to 0. And for all f in LP star 1 less than or equal to p less than infinity. Okay, that means that is integral a to b f of t cos n t tends to 0, integral 0 to a to b f of t sin n t tends to 0 for all such f, and that is cos n t tends to weakly to 0, sin n t tends weakly to 0 for all 1 less than or equal to p less than infinity. B. What is the weak limit of cos square n t? So cos square n t equals 1 plus cos 2 nt by 2, and that of course cos nt goes weakly to 0. So this is a constant function, so this goes weakly to half. So here is an example about weak convergence. If f converges weakly, fn and gn converges weakly, fn gn need not converge weakly to the same limit. It may not even converge weakly. So when you are doing non-linear operations, you have to be very careful. Here cos nt goes to 0, but cos square nt does not go weakly to 0. It goes weakly to half. So this is important point to note, and this is an example of how you should be careful when dealing with non-linear functions of weakly convergent sequences. Okay. 14. So a trigonometric series is a series of the form a0 by 2 plus sigma n equals 1 to infinity an cos nt plus bn sin nt. So typically the Fourier series are trigonometric series. So any such series written like this is called a trigonometric series. Okay, so rewrite it in its amplitude phase form, namely a0 by 2 plus sigma n equals 1 to infinity dn cos nt minus phi n. Okay, so this is called the amplitude. Phi n is the phase, dn is called the amplitude. Okay, so solution. So all you need to do is put an equals dn cos phi n and bn equals dn sin phi n, and from this you get dn square equals an square plus bn square. So you can compute dn, the positive square root, and once you know dn, from this you can, whichever relation you like, you can take tan of this is bn by an or cos phi n or sin phi n, but from whichever from these three equations you can easily compute what is phi n. Okay, so B. So this is called the Cantor-Lebesgue theorem. So Let E contained in R be a set of positive Lebesgue measure. If a trigonometric series star, so star is this one, converges over E, that means at every point in E it converges, then AN goes to 0 and BN goes to 0. So the coefficients of the trigonometric series have to go to 0. That's a necessary condition for the convergence on a set of positive measure. So solution. So without loss of generality, we can assume that the measure, Lebesgue measure of E is strictly finite, because it converges over a set E. So if necessary, you take a subset of positive finite measure, then also it's going to converge. So there's no problem in assuming that the measure is finite. Okay, so series converges. That means the general term has to go to 0. So this implies that dn cos nt minus phi n tends to 0 as n tends to infinity. This is the general term of the series, of any convergent series has to go to 0. So that is why we wrote it as 1, because we had two terms. Now we combine it and wrote an amplitude phase form, so there's only one term, and so it's sigma an, sigma alpha n, so alpha n has to go to 0. So that dn cos nt minus phi n has to go to 0. So this can happen in two ways. Either dn can go to 0, but if dn goes to 0, we are through, because dn is an square plus bn square is dn square. So if dn goes to 0, then an and bn automatically go to 0. So dn goes to 0 implies an bn go to 0. So this is what we need. So assume, if possible, dn does not go to 0. Okay, so then there exists an epsilon positive and a subsequence dnk such that dnk is greater or equal to epsilon, which is strictly positive. So it stays away from 0. Okay, so now if dnk does not go to 0, the general term anyway goes to 0. So this implies that cos nkt minus phi nk has to go to 0 for all t in E. Okay, so mod E is finite, so constant functions are integrable. So, and you have mod cos square nk t minus phi nk is less than or equal to 1, and therefore this implies cos square okay, and okay, so this is less than or equal to 1 and this is integrable, and cos nkt minus phi nk goes to 0, and therefore this implies that integral over E cos square nkt minus phi nk dt tends to 0. So that is what it is, integral over E of 1 plus cos 2 times nkt minus phi nk by 2 dt goes to 0. So let us look at this cos 2 times nkt. So what is cos integral cos 2 times nkt minus phi nk dt over E? This is equal to cos 2 times phi nk integral over E cos 2n kt dt plus sine 2 times phi nk integral over E sine 2n kt. That's equal to cos 2 phi nk integral over R chi e cos 2n kt dt plus sine 2 phi nk integral over R chi e sine 2n kt dt. Chi e of t, you can take chi e of t. Okay. Now mod E is of finite measure, therefore chi e belongs to L1 of R, and cos 2 phi nk sine 2 phi nk are all less than or equal to 1. Therefore, each of these terms has to go to 0 by the previous exercise. So, exercise 13. Okay, and this implies that cos 2 times nkt minus phi nk dt over E goes to 0, and that is a contradiction because 1 plus that by 2 goes to 0. Now this itself separately, this alone goes to 0, so that means it has to go to half, which is not, we have shown that it goes to 0 and therefore it's not possible, and therefore this is a contradiction. So this implies that dn goes to 0, that is an and bn both go to 0.